Okay, so welcome back to another video. So in today's video we have an infinite sum, and of course we also have with the Riemann Zeta function included. So the infinite sum of the Riemann Zeta of 2n divided by 2 or divided by n times 2n plus 1 multiplied by 4 to the power 2n. So we did something similar with this in a previous video, but so of course they had to add some extra terms to make things a little complicated. So well, I'm just saying similar because it's just the format looks similar, but it's not going to be the same method just like that last video. So now that begs the question, so how are we going to tackle this? So the way I'm going to start this off is I'm actually going to use a lemma and prove that lemma, and we're going to use that from there and then perform some algebra and then some even calculus too. But not only that, there's also a couple formulas and some theorems that have been used or discussed in previous videos, so that's something to just look forward to once we get to those steps eventually. Okay, so with that, let's start off with the lemma. So this lemma we're going to use this is actually known as the Riemann Zeta function for even integers. So this states that if we let x be a real number, also with the condition that the absolute value of x is less than 1, so then the following formula is given as follows. So we have the infinite series of the Riemann Zeta of 2n multiplied by x to the power 2n is equal to 1/2, and then subtract with pi times x divided by 2 and then multiply with cotangent of pi x. Okay, so now we're just going to get to the proof. So what I want to start with, so how I'm going to start off this proof, we're going to actually start with using Euler's infinite sine product, which of course I've derived this formulation or theorem before, and so if you want to view the whole calculation, whole procedural method and how I did that, then you can click to that in the link in the description below. What we're going to start off with is with that I'm going to actually replace the input for like our x with pi of x instead. So therefore, when we do that, the substitution we have is sine of pi x and then divide by pi x. So that's just equal to our infinite product. So this is going from k is equal to 1 of 1 minus x squared divided by k squared. So simply I just replace the inputs for pi x, and then coming down all together, then we get this the exact formula over here. So next I'll take the natural log of both sides. So that means I'll have the natural log of sine of pi x, and then we divide this by pi x, and then equal to the natural log of our infinite product series, 1 minus x squared divided by k squared. Okay, and so on the left hand side I can actually just use our rules of natural logs. So I can split this up as a difference of 2 natural logs since the input's under the division. So we have natural log of sine of pi x, then subtract with the natural log of pi x. And then on the right hand side, what I'll do is that because we can actually use the continuity of logarithms to rewrite the product series instead into a summation, an infinite series. So therefore we have the infinite sum going from k is equal to 1 of the natural log of 1 minus x squared divided by k squared. Now next, what I'll do is, well, before I get to the actual next step, let me actually just also add the natural log of pi x to both sides, so that then we get the same thing, just except we move this to the right hand side of the equation. It is now positive natural log of pi x, and then plus our infinite sum, k is equal to 1 of the natural log of 1 minus x squared divided by k squared. And now next, now the major step I want to do is let's actually take the derivative of both sides in respect to x. So when I do this, that means d over dx, and then natural log of sine of pi x, open parentheses, and then equals the derivative of the right hand side, natural log of pi x, and plus infinite sum, k is equal to 1, natural log of 1 minus x squared divided by k squared. Now the calculation over here is not too difficult. So, you know, natural logs is just for, on the left hand side specifically, it's just 1 over sine pi x and then the derivative of the input, so that's cosine pi x and then that input, so it's pi, so we have pi times cosine of pi x, and then we divide this by sine of pi x. Derivative of this, the right hand side, natural log pi over x is just 1 over pi x times the derivative of the input, which is just pi, so that'll just cancel out to just 1 over x. And then add this with, now we can actually take differentiation of inside the function of our sum series, so really we could just take the derivative of the natural log of 1 minus x squared k squared. So what that comes down to is that we have, of course, our infinite sum still being kept intact. And then now the derivative, so this is just 1 over this thing, so it's 1 divided by 1 minus x squared divided by k squared, and then we multiply this with our derivative of the input, so which is just using quotient rule, we get that this is just negative 2x divided by k squared. And now I'm going to perform 2 steps into one line. So what I'm going to do now is I'm going to rewrite cosine and then sine using your trig properties that comes down to cotangent of pi x. Not only that, I'll also multiply an x to both sides, so that way the x over here will just cancel just 1, but also that x will have to be added one more term, so that's an x squared. So now, coming all together, so pi times x, cotangent of pi x, then equals 1, and then plus, now sum series still stays the same. This is just 1, and then 1 minus x squared divided by k squared. And then inside this is negative 2x squared divided by k squared. Now the next step is that you'll see that what our sum series, let's just disregard what's in the parentheses on the extreme right hand side for now, but if we're looking at our infinite sum series, you can see that a similar formulation is that this is actually the same thing as rewriting it as a sum of an infinite geometric series. So what that implies is that I can write this as follows. So let me just keep the right hand side over here as the way it is. So this is 1, and then plus, now we now have 2 double sums. We have 2 sums, not double, 2 sums. So now we have that this is starting geometric series n is equal to 0 of this will be x squared and then divided by k squared, and then to the power n. And then still we multiply this with, of course, the negative 2x squared divided by k squared. Now what I can do for this next step is that I can factor out the negative 2 and put this outside of our sum series, our double sum. Not only that, the x squared and the k squared share the same base over here, so that means I can add the exponent plus 1, but I'm not going to do that. Instead, I'm just going to rewrite our index, so this time our index n starts at 1. So then over here, I'm going to rewrite what we just reiterate. We showed that so far pi x cotangent pi of x is equal to just 1, and then subtract that with 2, and then multiply with our double sum. So this is k is equal to 1, and now our double sum over here, we have that we changed our index. It's just now it's n is equal to 1 of x squared divided by k squared, and then to the power n. Next thing I'll do is that not only that I can distribute the n to both the numerator and denominator, I'm actually going to interchange the order of the summation, and this is actually, it's valid from Tonelli's theorem, which Tonelli's theorem is basically the same thing close to Fubini's theorem, except it just deals with like non-negative measurable functions instead of like a specific domain. So doing this, we have, let's see, so this will be 1, then minus 2, and then we interchange our sum. So now in front will be the n index, and then in our parentheses we'll have, so now even though when I said we distribute the exponent to n, I'm actually going to factor out the x to the power 2n outside. So really the numerator would just be 1. So let's see, infinity k is equal 1 of 1 divided by k squared, and then we multiply that by x to the power 2n. Okay, yeah, we write the same thing. So we have here n is equal to 1, and now you'll notice that inside the parentheses our sum series is actually the definition of the Riemann Zeta series at 2n. Right, 2n, thank you. And now with this, we can just replace in the parentheses with our definition of the Riemann Zeta function. So this will be 2n, and then multiply with x to the power 2n. And we're actually almost there. We want to show that our lemma, that the calculation, the infinite sum of Riemann Zeta 2n times x2n is equal to 1/2 minus pi x2 times cotangent pi x. So now the rest is history from here. You'll see that I can subtract a 1 and then also divide a -2. So then we see that if I'm just gonna skip the steps, I can actually rearrange the terms since it's undercommutative with addition / subtraction. So we get that the following result is that we have 1/2 minus pi x over 2 and then cotangent pi x is equal to the infinite sum, n is equal to 1 of our Riemann Zeta 2n and then x to the power 2n. And that proves the lemma over here. So now next thing is that we're going to use this lemma and then jump our way forwards into evaluating this series. So the thing I'm gonna do is I'm actually going to let our infinite sum equal to f of x. So here, let me draw it like this. So this is going to be our f of x. And so the whole thing is f of x over here. How about I do it like this? Since this whole thing is under the equality, I'll actually just draw this little brace, signify that this whole thing is gonna be the f of x. So then what I'm gonna do with this is actually I'm going to divide x to both sides. So when I do this, so let's actually move on to the next step. Let's actually write this out in black. So now we have f of x divided by x. And so that is equal to, so we write our infinite sum, n is equal to 1 of the Riemann Zeta 2n divided by x. So share the same base. Basically, I'm just subtracting a 1 of the exponent. So this is x to the power 2n minus 1. Next is now just divide everything by x over here. So then this is equal to 1 over 2x. And then this will be subtract with pi over 2 and then cotangent of pi x. What I can do from here is that jumping to the next step. Now what we can do is that if we set some arbitrary value y, so that such that it actually stays between the interval 0 and 1, what we can do there is that we can actually integrate our f of x divided by x from 0 to y, and so we can obtain another result between that interval from 0 to 1 in our value y. So what this means is that I can actually take the integral from our bounds from 0 to y of our infinite sum of the Riemann Zeta 2n and then x 2n minus 1 dx, of course. And then I'll integrate that from the right hand side as well. So 0 to y of, let's see, 1 over 2x and then minus pi over 2 cotangent pi x dx. And now what I can do is that, of course, simply I can actually drag the limit outside, or I mean drag the summation outside, and really we're just left to evaluate the integral from x to the power 2n minus 1 simply due to absolute convergence. We have n is equal to 1 and then 2n, then the integral from 0 to y of x to the power 2n minus 1 dx. And then I can actually split this into two integrals over here because it's basically due to linearity. 0y, 1 over 2x dx, and subtract that with 0y, pi over 2 cotangent pi x dx. And when we do this, then let's see, moving on to the next step, we perform the calculations out. So this will still be Riemann Zeta 2n, but then we have x to the power 2n and then divided by 2n from our iterated bounds from 0 to y. And then of course there's the right hand side. So we get that this is just 1/2 ln of x from y to from 0 to y, and then we subtract that with over on the right hand side again. So this is 1/2, then the natural log of sine of pi x from 0 to y. And then you can calculate this simply just by doing the integration by parts, but I decided to skip that step. Now, once we calculated these bounds, so this is going to be different, especially from the right-hand side too, because we have a natural log, and then we have to evaluate it at 0. So you know that natural log of 0 is not defined. So we have to, if we're going to do something like this, we actually might as well convert these into limits. But first, before we get to that step, how about now let's calculate the right-hand side. Get that, by the way, this arrow just supposed to signify the next step, not whatever was in the orange. So, okay, n is equal to 1 and then to infinity. And so we have the Riemann Zeta of 2n, and then we divide this by, well, of course, divide by n, and then we multiply with y to the 2n. This is supposed to be a 2n over here. I went back to my notes and I messed up a little bit. That's okay. Okay, so now that's the left-hand side. So now we gotta calculate the right-hand side. I'm also gonna jump a couple steps further because simply we see that there's a 1/2. So I'm actually going to factor out that 1/2 and then combine some of the terms over here. So then we have 1/2, and then that's being factored out. So we can multiply this. We have ln of y. Next we have the limit as x approaches 0 plus, so it's coming from the right side, of the natural log of x. Okay. Subtract that with the natural log of sine of pi y. Okay, and then add that with the limit as x approaches infinity, or x approaches 0 from the right, of the natural log of sine of pi x. And now the next step is that I multiply 2 to both sides. So of course the 1/2 will not only cancel, but also the 2 from the denominator will cancel as well. And now the next step from, since we got rid of the 1/2, now we just have to combine our terms using the, our rules of natural logs, of course. So let's see, we have okay, so let me just continue on writing forwards. So we have the infinite sum, so n is equal to 1, Riemann Zeta to n, and now it's divided by n, and then y to n. Simply we have that we take the natural log, so this is the natural log of y, and then corresponds with sine of pi y, and then also we're going to add the limit as x approaches 0 plus, well, really I could just say 0, honestly, so it wouldn't really do much, honestly. Of the natural log of this will be sine of pi x, and then divide by x. What I can do from here is that I want to manipulate this equation just a bit. So how can I do this? I can actually rewrite this as I can actually multiply and divide a pi to both the numerator and denominator. Yeah, right here should be good. So let's see, if I write this, the limit x approaches 0, and then multiply and divide a pi sine of pi x, and then divide by pi x, right? Okay, and then we can use a little fact that we know is that if I take the, yeah, right here should be. If we know that the limit as x approaches 0 of sine of x divided by x is equal to 1, we'll use that fact simply because there's a pi x and a pi x. So once you follow this fact with the input, the result's going to give you the same. So basically, this is just pi. Yeah, the input is just pi on its own, and therefore we're just going to get ln of pi. So therefore, over here, this is the same thing as the natural log of pi. Now we have, we take this limit, so we showed that this is actually, we could actually rewrite this as natural log of pi. Then we can continue further by rewriting the natural log rules. So let's see, rewrite this again. N is equal 1, and then Riemann Zeta to n y to n. Then that's just equal to, so I'll take the, let's see, natural log limit. So that means this can be written as pi times y, and then divided by sine of pi y. Okay, so what now? So far we showed that we have the respective expression from the left and the right. I'm actually going to call this function capital F of y. So what we do from here is that now the next step is going to be interesting. What I'm going to do is I'm actually going to integrate this entire thing, like from both expressions, and then we're going to integrate it from the bound between from 0 to 1/4. So simply, basically, we kind of like treat this as like our antiderivative to get, in order to get the respective answer for our Riemann Zeta function, infinite sum, dy. And so we integrate this 0, 1/4, n is equal 1, and then Riemann Zeta 2n divided by n, y 2n dy, and then equals 0, 1/4, natural log of pi y divided by sine of pi y. And of course we could do the same thing from this side. What I mean was I of course move the summation outside, and we have our variables, and it does not depend on the integration variable, so that goes outside as well. It's like a constant. So really we just have goes 1, then zeta 2n divided by n, and then the integral 0, 1/4 of y 2n dy. And then of course we can actually just use our rules of natural logs and use linearity to integrate two different integrals. So 1/4, and then we have what was it? Natural log of pi y dy, and then subtract that with the integral 0, 1/4 natural log of sine of pi y. Of course, now you just evaluate our bounds. Well, from the right hand side, we're going to do what we can. So let's see, 2n divided by n, and then over here we have, this is just, let's see, plus 1 divided by, so we have y to the power 2n plus 1, then divided by 2n plus 1, 1/4, 0. And then over on the right hand side, well first, how about this? Let me just evaluate our bounds here before we move further, just so we get what we want. We get what we want to do. So infinite sum, n is equal to 1, the Riemann Zeta 2. So let's see if I plug 1/4 for y. So that would just be on the bottom, and then base 2n. Yeah, so it would just be in the denominator we have n, and then 2n plus 1, and then 4 to the power 2n plus 1, all with the numerator that is the Riemann Zeta of 2n. And then I'm actually going to jump the gun and just perform the full calculations on the right hand side without actually having to do each step by step. So over here, this will just be 1/4 ln of pi, and then minus 1/4 ln of 4, and then we subtract this with 1/pi, and then the integral from 1/4, is it 1/4? No, this time pi/4. And then this time we're actually doing a u-substitution, so I let t equals pi times y. Then we changed our bounds of integration as well. So that will become the natural log of what is it? Sine of t dt this time. Of course, we have to calculate this. That's too much work, and I can actually just justify by saying that I actually integrated this integral over here from a previous video. So if you want to check that out, the video to that will be in the link in the description on the full derivation and calculation of finding the exact value over here. I'm skipping that step. So what that comes down to, I'll say, is that this integral over here is actually equal to -c squared, or -c divided by 2, and then subtract with pi/4 ln of 2, where c is defined as Catalan's constant. I'll put ct for constant. That number is actually, you see that a lot in number theory, I believe algebraic number theory, and of course combinatorics as well. So you'll see that number a lot, heavily used in it. But comes out of this number, but now we can actually just we're actually almost done, really. So coming down, we have this is we write the same thing. So I have 1/4 pi, or excuse me, ln of pi, and then subtract 1/4 ln of 4. Oh yeah, I almost forgot. There's supposed to be a minus 1/4 over here, so I'll put that down. And so minus 1/4, and then minus 1 over pi, and then substitute that with our Catalan's number, and then, really the whole evaluated integral over here. So this is negative c divided by 2 minus pi over 4 ln of 2. Okay, and then we can actually just substitute some stuff. What I mean is not really substitute, but distribute. So ln of pi, then minus 1 over 4 ln of 4 minus 1 over 4, and then of course we have plus c divided by 2 pi, and then plus 1 over 4 ln of 2. Now if we simplify some stuff out, let's see, we have a ln of pi and then an ln of 2 over here, and of course an ln of 4, so that means ln of 4 and then divided by 4, so we have ln of pi over 4, and then we have a plus ln of 2, so that means this will be 2 pi divided by 4, and that will reduce down to pi over 2. So we have 1 over 4 ln of pi over 2, okay? And we're just left with, of course, minus 1 over 4, and then plus Catalan's number divided by 2 pi. Now the last step is that all we have to do is, let's see, so we showed that on the left hand side this is the Riemann Zeta function. So let's see, from over here to here, I'll write that this is equals, so we showed that this side is equal to this side, but what we want to achieve is what are given here. See, notice that there's a 4 to n, and over here we have the base 4 to n plus 1. Really, last step, just multiply 4 to both sides. Then the 4 will cancel out from with the 1, so we're just left with 4 to the 2 base 2n, and then everything here will just go away. So therefore, justify this step, multiply 4. So then we get that the final answer is just ln of pi over 2 minus 1, and then plus, let's see, 4, so that means this will be 2 times c divided by pi, like so. And there we have it, the final answer in this orange box. Alright then. Now that's pretty cool if you ask me.